All right, today we're starting into chapter 4, types of chemical reactions and solution stoichiometry. Okay, so one thing you're going to notice is that water is a pretty common solvent. You're going to use it for a lot of your labs, your reactions. Uh, it's able to dissolve multiple substances. So the reason it's able to do this is first off, it's a polar molecule, which means it's going to have regions of partial positive charge and regions of partial negative charge. You notice here that your partial positive charge is going to be on the hydrogens. Your partial negative charge is going to be on the oxygen. Uh, you'll learn more about why that is along the way. But if you notice down here, we have an electropotential map that also shows you the negative and positive regions of water. Your negative is your red regions, your positive is your blue region, and these symbols for the partial charges is a lowercase Greek delta. So see, you've been mathematically you've been using the capital delta, and now you're just going to use the lowercase delta. Uh, when water interacts with ionic compounds, the ionic compound undergoes what's called hydration. And so hydration is when water is going to come in, and here you see a block of sodium chloride or common table salt. And you know, sodium chloride is an ionic compound with sodium ions and chloride ions. And so the water comes in, and the negative region of water starts picking off the positive sodium ions and separating them from the salt crystal. The positive regions of water are going to come in and start interacting with the chloride or the negative ions of sodium chloride and pulling them away. And then those ions are going to get wrapped in little shells of water so they can't interact with each other again. And so your ionic compounds aren't just going to dissolve in water, but the compounds themselves are going to be their ions are going to be pulled apart. Later on, you'll find out that water is also a good common solvent because it undergoes multiple intermolecular forces, but that's more of a semester 2 type of thing. Just know that that's the case. Okay, so when we're talking about aqueous solutions, we have a couple of words we need to know. The solute is the compound that's being dissolved. The solvent is the substance that does the dissolving. So again, if we put salt in water, you notice that salt is your solute, water is your solvent. One thing that can characterize solutions is their electrical conductivity, or how efficiently they conduct electricity through the solution. Uh, and this is going to really be dependent on the electrolyte properties of the solution. So strong electrolytes, ions move freely through the solution. There's a good number of ions in solution, and they conduct electricity very well. Weak electrolytes, you're going to have less ions in solution. Uh, you're going to have a weaker conduction of electricity. You're only going to get partial dissociations of your compounds in solution, which means so it's like in a strong electrolyte, you get full dissociation of compounds. So like your sodium chloride, all of your salt is going to break apart into its ions. With compounds that are only partially soluble, uh, you're going to get some ions that'll break apart, but then the rest of it stays in its neutral molecular form. So you're only going to get partial dissociations, and that's going to lead to weak electrolytes. So if we're talking about strong electrolytes, so again, these have compounds in them that completely dissolve in solution or completely dissociate. But there's some main types of strong electrolytes to look at. So soluble salts, strong acids, and strong bases are going to be your main strong electrolytes. Solubility of salts, for example, is going to have specific rules. Now, I've given you a list of these rules that you can use as we talk about solubility throughout the summer or the semester, depending on when you're taking it. But the when you use the solubility rules, you want to make sure you use them in order. So it's like if one rule down the list says that the compound is insoluble, but rule one or two says it's soluble, then you go with rule one or two. So these rules are in a hierarchy. So I've given you some to reference back to when you're trying to figure out if something is soluble. So it's like here, group one alkali metal cations are always soluble. So, like, let's say I had the salt lithium chloride. Okay, well, I know for a fact that's going to be soluble because of the group one cation, which is lithium. Ammonium compounds are also soluble. So compounds where ammonium is your cation. Let's see, nitrates, acetates, and perchlorates are going to be soluble. Specific halides, so your chloride, bromide, iodide are going to be soluble. Now here you see there's going to be some exceptions. So if I have like silver chloride, silver is one of my exceptions, that's not going to be soluble. So anytime you see an exception, just make sure you're making note of that. So here again, we talk specifically about silver, but exceptions are like silver nitrate or silver acetate. Those are going to be soluble. So you really want to make sure you're using the list when you're trying to figure this stuff out. The list ends up going down to like 11 different rules. And this isn't something you would have to memorize. It's something you may need to have, for an exam. It's, but yeah, when I do exams, you're able to use notes, so you would be able to have these. But you just want to make sure you go through these and understand them so that you can use them when you need to. And again, you use them in order. So let's see here. If Rule 10 says something's insoluble, but Rule 1 says it's soluble, well, then we go with Rule 1. So strong acids are another type of strong electrolyte. Strong acids fully dissociate in water. General equations for a strong acid. So the way we represent this is you have your proton and then whatever else is on the acid. And so your HA is your acid. You mix it with water. The water will take on that proton. You'll get a hydronium. And you're going to get the negative ion from or later on, I don't think it's this semester. Again, it's a second semester thing, but conjugate base of the acid. Now, I put another generalized equation down at the below that, which is the dissociation of your acid into a proton and the negative ion from the acid. I did this, these two are the exact same thing. You can use these types of formats interchangeably. Again, you're going to see chemistry use this second one quite a bit as a shorthand, knowing, as we talked about, that these protons don't just exist in nature. What you're actually getting when you mix an acid into water is you're going to get these hydroniums that are acting as your protons. So, as you can see here, if we look at a real acid, we have hydrobromic acid. That's going to be a strong acid. It's going to fully dissociate, which means all of the hydrobromic acid molecules are going to break apart into protons and bromide ions. And so, again, this is a dissociation equation, but you know that this species actually exists as hydronium. And that's what we mean by aqueous. Aqueous means dissolved in water. So start wrapping your head around generalized equations and and how those relate to actual acid equations. So here's some strong acids for you. Now, some acids are going to be multiprotic acids. So protic multiprotic means that an acid has more than one proton. So here you have sulfuric acid, that's a diprotic acid. Di is the prefix for two, so there's two protons on the sulfuric acid. That doesn't necessarily mean that this strong acid is going to put more ions into solution than, say, hydrochloric acid. Because what's going to happen every time you have a multiprotic acid is you're going to start here, you're going to get a single deprotonation. So a proton is going to go from here to water. You're going to get your hydronium, and then what's left over is going to be the HSO, the hydrogen sulfate ion. So you see one of the protons was dissociated, and now I have protons in solution and hydrogen sulfate. And could that hydrogen sulfate put another proton into solution? Yes, it could, but it's very, very unlikely, which will make more sense to you again in second semester when you deal with what are known as chemical equilibria. So just know that just because an acid is multiprotic doesn't necessarily mean it's going to be a better electrolyte because it has more ions in solution. So strong bases are another type of strong electrolyte. And your strong bases are going to typically be your group one and group two hydroxides. So your group one, group two cations, and then hydroxides. So here's like a lithium hydroxide, that's group one. So these three here, group one, these three here, group two. So all of these hydroxides are strong bases. So your basic idea is you have your base and your hydroxide. Your hydroxide will dissociate. Oh, let's see, that's not exactly right. So here, this should have an N in front of it. But you'll have your positive cation left over, and you'll have however many number of hydroxides in solution. So here, you notice that your calcium hydroxide fully dissociated into your calcium ion and your two hydroxides. So again, you get a full dissociation. So the way to think of it is Arrhenius talked about this. An acid is a compound that puts protons into solution and so effectively increasing the concentration of protons in solution. And Arrhenius, and he said the reverse. So about bases, he said they put hydroxide into solution or effectively increase the concentration of hydroxides in solution. So next we can look at weak electrolytes. These are going to be compounds that only partially dissociate. So predominantly your weak acids, weak bases, some partially dissociating salts can also be weak electrolytes, but that's you're not really going to deal with that too much at this level. But just think of your weak acids and weak bases. So here, HNO2, I hope you're able to name this nitrous acid because you have the nitrite ion, but you notice that it is going to dissociate into proton and nitrite ions. However, notice the double arrow. It's no longer just a single arrow. This double arrow is in chemistry, this is an equilibrium. And so that means so when this compound doesn't fully dissociate, it reaches a point where the neutral HNO2 molecules are dissociating as fast as these protons are recombining with nitrite to go this way and reproduce the compound. So you're only going to get a certain amount of ions in solution. You're not going to get all of your nitrous acid molecules to dissociate. It works the same way with bases. So a weak base will interact with H2O and take a proton to itself. So a proton is going to go that way, and then you're left with a positive species and your hydroxide in solution. And so a good example of that here is C5H5N. This one you wouldn't need to know the name of right now, but just make sure you can look it up. This is called pyridine. It's going to react with a few water molecules and take a proton, forming pyridinium and hydroxide. So this is kind of your first look at an organic molecule, your pyridine. is a ring structure. Have your lone pair there, double bond. And then what's going to happen is your H2O will be out here. One of these, well, actually, let me draw this like let me draw the molecule. These will make more sense as we go on. That's a Lewis structure. So this proton here is going to be taken over to that lone pair, and you'll be left with a hydroxide and pyridinium in solution. And so, but this is going to again reach an equilibrium where you're getting pyridinium being produced at the same speed as pyridine being reproduced by the pyridinium shedding its proton and giving it back to hydroxide. And that's going to bring you back over here. So again, you want to think about partial dissociation, which means that so whenever you put the weak electrolyte in solution, it's not going to all go into making ions. And then of course you have non-electrolytes. And these are compounds that when dissolved in water, they don't produce any ions, they don't conduct electricity. A good example is dissolving sugar in water. And so here, a good look for you, this is your glucose molecule with its formula down below. You'll find that glucose and fructose have the exact same chemical formula. The difference is glucose is a six-membered ring, where fructose is a five-membered ring. But notice here how we just have the solid molecule, we dissolve it, and now it's dissolved in water, but you notice none of it broke up. So it's just sitting there in full, like it dissolves, it disappears, but it's the molecules themselves don't actually break up. And so you're not getting any ions in solution. So this is a non-electrolyte. All righty. Now, this is a concept you really want to start wrapping your mind around. So composition of solutions. One of the ways we can look at that is through a concept known as concentration. And so concentration is going to be predominantly represented as molarity. And so you want to make sure you get this down. So your molarity is going to be moles of solute, so whatever you're dissolving in solution, per liters of the whole solution. And your units are moles per liter. You really want to get this down because you're going to be using this in a lot of different calculations. Let's see. So when you're talking about a solution in terms of its concentration, here you see that you have a 2.5 m. That's how you would write it. You would say that it is 2.5 molar, which means that you have 2.5 moles of some compound per liter of a solution. So start getting used to this type of this type of format, this formalism, so that it makes sense to you as you're solving solving exercises. So let's start into that. So we have a solution of ethanol mixed into water, and that's prepared by dissolving 75 milliliters of ethanol. And you see the density of ethanol is 0.79 grams per cubic centimeter. And you dissolve it in enough water to make 250 milliliters of your solution. And so you're also going to have to start thinking about that. Well, how do I actually make a solution that's say, I don't know, 100 liters of a 2.5 molar solution? You'll have to figure that stuff out. So what is the molarity or the concentration of the ethanol in this solution? So uh, make sure you're getting this when you do your assignments. You want to talk about quantities that you know. You want to talk about what is the exercise actually asking you for. So in this case, And you can say, well, the density of our solution is 0.79 grams per cubic centimeter. I know I'm working with molarity, and so I'm going to need things in liters. So my conversion, I remember, I'm writing down things that help me solve the problem. 1 milliliter is 1 cubic centimeter. The volume of my solution is 250 milliliters. But I notice that density gives me a mass, but I'm going to need moles, which tells me I'm probably going to have to figure out a molar mass. So what? For ethanol, we have carbon, we have hydrogen, we have oxygen. And this is a pretty decent list to help me solve the problem. And then, of course, the exercise itself is asking me for what is the molarity? What is the concentration? Okay, well, I'm going to start by reminding myself what this is. So molarity, moles of solute per liter of solution. In our case, that's going to be moles of ethanol per liter of solution. Okay, and because 1 milliliter equals 1 cubic centimeter, I know that my density goes from 0.79 grams per cubic centimeter to 0.79 grams per milliliter. Okay, so let's figure out the molar mass of ethanol. That's going to be 2 carbons plus, nope, not 5 hydrogens. You have 6 hydrogens plus an oxygen. That's 2 times 12.01 plus 6 times 1.01. And I'm still doing this whole process to figure out molar mass right now. I want to see you do this up through chapter 4, but then once we get beyond that, you can just write down what the molar mass is, probably up here in this box. You can make a list of molar masses you'll need to solve the problem, because once we get past chapter 4, I'm pretty convinced you know how to do this. And we add this all together. Get it 46.08 grams per mole. Now, I need moles of methanol. I already have my volume. Okay, so what do I have? 75 milliliters of ethanol. I've been saying methanol. Methanol is 1 carbon. Ethanol is 2 carbons. And it's funny how sensitive chemistry is. Ethanol is, of course, it's another organic alcohol. And if you start going up the list, methanol, which is a 1 carbon alcohol, if you drink that, death. Ethanol, it's a 2 carbon alcohol. Well, that's what you find in most of the drinks people will get at a bar on a Friday night. So enough of it causes death, but not right off. However, then you go up to propanol, which is 3 carbons and death. So it's really funny how sensitive chemistry can be. So then we want to get this to moles. So we're going to step through density. I know because I have milliliters of my ethanol, but I know that I have 0.79 grams of ethanol per milliliter, which of course now we see that milliliter slides out. Well, but now that I have grams, I can divide by the molar mass, Okay. And when I multiply this all up, because again, grams divides out, this is going to give me 1.3 moles of ethanol. Okay, now I'm ready to figure out the molarity. So my volume, I'm going to remind myself that my volume is 250 milliliters, but I need moles per liter. So I figure out that this is 0.250 liters. And now my molarity, that's going to be my 1.3 moles per 0.250 liters. Or when I divide 1.3 by 0.250, I get 5.2 molar. So again, that capital M is moles per liter. So one thing you could, again, one thing you could do in chemistry is you could say, what do I have? What are the units of the thing I need to calculate? How can I put the numbers I have together to make that happen? All right, so for the next exercise, we're going to make this a little more intense, but I'm doing this. I want you to learn how to do this. You're going to do assignments where you do this because, and you'll see what I mean in a minute. The reason we do this is learning to solve problems the way we just did the last one is all well and good. However, we're entering a world where AI can do that. Just being a calculator is not going to guarantee you a job anymore. What I'm about to show you is the ability to abstractly model a system. So to be able to think multidimensionally like that, to model systems, to take these physical systems and understand them at a deeper level, is to understand them intuitively, is something that will make you marketable instead of just having someone think in the future, well, I could just replace this person with AI. So I know it's not going to be your favorite thing, but we are going to do this at a much higher level. So here we have 100 milliliters of a 0.875 molar potassium carbonate. Let's see, it's sitting uncovered. After a while, some of the water in the solution evaporates. And the next day, you find that the potassium concentration in the remaining solution is 2.334 molar. What volume of water evaporated from the original solution? So, so let's go through our list of knowns that are going to help us first. We know that our initial volume is 100 milliliters. Our initial concentration and this is the concentration, this molarity is the concentration of the compound we put in. Now we're going to use a different symbol for concentration of potassium ions. So when you see square brackets like this, in chemistry notation, this means concentration, and you're still going to get units of moles per liter. But we need a different value to make sure we set these two numbers apart. So our final concentration of potassium ions is going to be 2.334 moles per liter. And yes, I'm throwing terms at you that you'll learn more in depth later on. The reason I'm doing that is a lot of stuff we do in science is, again, it's like learning a language. I'm just kind of tossing you into the immersion. And if you look at the brackets right now and go, what does that mean? Just keep telling yourself it's concentration. And as time goes on, you'll pick it up and eventually you'll see it and it'll make sense to you. So again, the whole point is to be immersed. What this problem is asking us for is, what is the change in volume? Because, and if you see me switch to a different color, this would be something you wouldn't have to write down. write down in like an assignment or whatnot. But the reason I say this is asking for delta V is we know that molarity is going to be moles over volume, moles per liter. And so as we notice, this concentration changed, and we know for a fact your moles of potassium ions are not going to change. So what has to change is the volume of the solvent, so the water. Okay, so the first thing I want to know is I have my expression for final concentration of potassium ions. What is an expression for initial concentration of potassium ions? Okay, well, I know that I have a molarity of K2CO3, so that's going to be moles of K2CO3 over, so per liter of solution. And I also know that for every 1 mole of K2CO3, I'm going to get 2 moles of potassium ions. So my moles of K2CO3 will multiply out. But I also know that this entire expression right here is my initial concentration. So that means my initial concentration of potassium ions is going to be 2 times my initial molarity. Okay? Now, in chemistry, lowercase n is very often number of moles. So it's just another notation for you. So I can say that in general, concentration of potassium ions is going to be moles of potassium ions. So that's what the subscript represents over volume of the solution. And now we know these do not change. So I can say that my expression for moles of potassium ions equals so I'm going to use my initial value, concentration times volume, because again, what you're doing is you're taking this volume and multiplying it to the other side. But this also equals my final concentration of potassium ions times the final volume. Because again, we can say this because the moles of potassium ions do not change. That's why my initial value equals my final value. Because again, if I was just to do this in general, multiply that through, and so again, you just see that that can be both the initial and final value because the moles don't change. Okay, so now what I'm going to do is I'm going to take this here, which matches this here, and substitute in 2 times my initial molarity. So that's going to be 2 initial molarity times initial volume equals, and I can solve this for my final volume. Okay, now Remember, I'm solving for delta V. So what is delta V? We know, hopefully, that a delta is your final minus your initial, okay? However, and again, I want you to work on wrapping your mind around this. Concentration as water evaporates is going up. But also, as water evaporates, volume is decreasing. So that means if volume is decreasing, delta V is a negative number. So what we're going to do to make it a positive number is we're going to flip the VI minus, to make it V initial minus V final. Now, what this is going to equal, if I have V initial minus V final, that also means I'm going to have V initial minus because up here I have an equality. And so I have to do the same thing to both sides of the equation. If I put VI minus V final there, well, then I have to do the same thing to this side. And that's where this comes from. All right. So now this is my delta V. And what I'm going to do is I'm going to pull. Now, if you were doing this in an assignment and you stopped here, that'd be fine. Like if you stopped with this expression, I would take that. But you can simplify this. If I pull out V initial, I get 1 minus 2 times the initial concentration over the final concentration of potassium ions. So now we've actually derived a formula that will solve this system. You are going to do this in homeworks, and usually what I'll do is I'll tell you, I'll give you some hints as how to get there, but then you're going to have to fill it. I'll give you hints like, well, it'll depend. Like, I'll give you hints like this. I may give you something like this, and then I will give you the final equation, and you have to fill in this middle section. So you're going to be practicing that because the whole point of your education now is you're going to be coming out more advanced than previous generations because that's the evolution of where we're going to. You're going to need to. So we're just going to meet it head on. Okay, so now that I've actually derived this formula, I can plug in numbers. Okay, so VI is 100 milliliters. You need square brackets because I'll have to use parentheses inside. Then 1 minus 2 times my initial concentration over my final concentration of potassium ions. All right. And so when I calculate this all up, delta V is going to be 25.02 milliliters. And that's how much water evaporated. Now, let's go back up. Let's say you didn't do this step here where you switched the VI and VF because you didn't realize that delta V, since it was an evaporation, was negative. Okay. What you would get for your answer is a negative 25.02, which would also be fine. I would accept that as an answer because positive and negative in this case, you're going to have to start thinking about them in terms of volume increasing and volume decreasing. Well, that's fine. This is an evaporation. So if you didn't do that step where you switched the delta V around to turn this into a positive number and you ended up with the negative, that's fine because again, the negative is representing what is physically happening. And what is physically happening is water is evaporating and the volume is decreasing. So if you miss that step when you're doing this later on, no big deal. But I just want you thinking about this. So I want you going back and reviewing what we did here because I want you to start to wrap your mind around how to do this because you're going to be doing it. All right, so we will continue on with chapter 4 next time. Not sure if that'll be tomorrow, but definitely Monday. And I will talk to you then.